Hello guys and girls, and welcome back to my video where today I'm going to be explaining to you guys Maze 2. Well, you might be asking yourself, well, didn't we just do Maze 1 a couple weeks ago, and you didn't publish the video? You're right. I was busy. So let's go over Maze 2. It's quite similar to Maze 1. In this case, we're actually going to be using portals to find the shortest path. Well, in this case, we're going to be using Dijkstra's algorithm as well. So it's one of the requirements that we need to do. Alright, so let's get to it. So what are the first steps that we need to do? Well, I made a little guide for you guys. A little guide on what we need to focus on. So we need to focus on the vertex, the portals, Dijkstra's algorithm, and the relax function. So let's get started to it. So let's say, for example, we have this certain maze. Correct. Let me change colors here, and color is going to be, let's make it blue. Let's see if my pen works. So let's see. So let's say this is the shortest path right here. That would be the shortest path. Now, how would we create this? Well, it's quite simple. So, each vertex is known to be a space. So right here, there's going to be a vertex, a vertex, a vertex, a vertex, a vertex. So each space will contain, each space you'll be creating a vertex. Now, we know what these are. We know what the vertex are. So what I recommend first is check your start and your end. So how do you do this? Well, each start and end, they're going to be located in the first column, the first row, the last column, the last row. And similar to what you did in Maze 1, you're going to be connecting them. Now, what is the method of connecting them? Well, that's a quite simple way to do it. Now, let's say you have this space right here. Let's call this one. And we have this one. So we have these two vertices. I want to look up and left. And left. Oh god, it's erasing. Let me hold it better. Up and left. So that's the only thing I'm checking for. I'm checking, hey, is there a vertex above me? Or in my left? Because each time you're going through the maze, you're always going to be checking up and left. You're never going to be checking right and down. For specific reasons, you will not do that. Because, well, you're moving to the right. And each time we're in the current one right here, we would check up and left. But in this case, since this is row 1, we don't check anything because it's the first row. There's nothing above it. Now let's say I come here, I check up and left, nothing here, I check here, up and left. Well, I have a connection with this one, up and left. I have a connection with this one, up and left. And then I iterate it until I hit this place, I check up. So you see the connections that I made. It's going to be looking like this. Doot, 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 doot. And let me illustrate it of what I'm checking. So what I've checked is my up and left. 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 And you're obviously doing a directed at. A basic edge, because you're connecting them both. I believe, right? Is this directed or basic? Let me look at the code. Looks like it's a basic edge. Now, a simple thing that you're going to be doing is, well, the weights here. Now, you're using Dexter's algorithm. What would the weights be in this case? Well, each one will have a weight of 1. 1, 1, 1, 1, 1. So what I recommend in this case with the verdicts is to have some sort of weight condition. You know, you're giving this class called verdicts. Well, you can modify it. You can add the weight that you want, and boom, that could be something that you'll be using. If not, you can be using something else. This sort of algorithm is all optional to you guys, but all you need to know is that you need weights. So how I have my my algorithm set up is that each vertex I create, the basic edges all contain a weight of 1 if they're only empty spaces. Now let's get into the condition that, let's say, hey, these portals look kind of funky. Well, let's go into portal sections now, because you guys understand how to create normal vertices. Now, let's say we're given this portal. What would we do? Well, I could tell right away that that I have a vertex here and a vertex here. But what are these numbers? Well, that's the weight that they're given. There could be a weight of from 0 to 9. So let's say this could be 9, this could be 9, the ones. That's the weight it's given. Currently, they all have the weight of 1, empty spaces and non-empty spaces. I mean, empty spaces have a weight of 1. Non-empty spaces, depending on the character, you'll have to modify the weight. So just give it a weight of this. So what I recommend right now is separating the work. First things first, get the vertices, empty space only. Then get the vertices of... Okay, you first create the vertices for empty spaces. Then you're going to be creating the vertices for the portals. Okay, so let me rephrase that again. So I'm going to go through the map maze. I'm going to create a vertex here, a vertex here, a vertex here, a vertex here. So 0, 1, 1, 0. So as I did regularly, I'm going to connect these first. This is going to be my first iteration of the maze. I'm going to create these vertices and link them together. Create this one, link it together. Ah, there's a hashtag here. I can't do anything. So let's move on. I have this vertex here, link them together. I have this vertex here, link them together. Am I linking the portals right now? No, I'm not linking the portals right now. That's a different task. So, let's link the portals. Now, I have this portal, and I have this portal. What I do is, hey, you can do this several different ways using, I don't know, vectors, arrays, unordered maps, whatever you guys want. Just keep in mind that you have, 10 characters you're working with, 0 from 9. So, the case being is, does this portal exist? You can make a Boolean array. So, what I'm saying is, I'm gonna make a portal set. So, it stores the information like, hey, I've iterated through the map, boom, 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 and I found this portal here. Can I find a match? So I save this information in my, I save that information in my vertex set. I save this information in a vertex set or a portal set. So, I can assign this to a portal array. And it contains the information of a vertex set, such as the location of where it's at, inside this position. Because you're using two things. The vertex set contains all vertices, including the portal ones that you created, the empty ones that you created, and that's it. And depending on how you have it set on the unordered map, or whatever you guys are using to find these guys, you will be getting the rows and columns of it and keeping track of where it's located, this information. I hope it makes a little bit more sense. So, let's say I moved through the portal, I found this guy. Hey, can I get the vertex information of this row? Well, I can tell this is row 2, column 2, or so let's just do 22 for right now. And this information is stored in vertex set. All right. So I store this information, this row and column, with the character itself. So I have, portal set, and I give it, 1 for it is an example, and I set it equal to true, or set it equal to a number. It could be this actually, it could be 22. And now I iterate again until I found this one. Well, I found this one, and it has the same character as this one. It's set to true. It has a number. I can pair them up together. So what you're doing is, you're finding this portal first, and then you're finding the next portal as you're going on, and you're keeping track of this in a list, in some sort of way. And if you do find them, let's say this is 1, hashtag 1, 0, 0. Well, I have a portal here. These guys are connected. So, you know how portals work. I go into my, 5th dimension, and I pop them in right there. There's the link between them. So, in most cases, let's say I have 2 here, and it's all connected. Well, what happens if I have this portal 2 here? Well, that's for you guys to figure out. Because if you guys can't figure out what I'm trying to explain here, try to visualize what's going to happen in the program. Alright. Now let's get into our final steps. Now, what is Dijkstra's algorithm? What is a relax? Well, you guys have learned this in class. So, what we're going to be doing in Dijkstra's algorithms is setting every single point to infinity. So this is for just, the current thing that you're going to be doing. So you know how you guys in class do the infinity, and then you relax them. Similar to that. You're going to make all the weights in your vertex set, or a temporary weight in your vertex set, in infinity. Any number would work. I do my 9,999, should work. And then you will be needing your min priority queue. If you guys haven't solved for that, then please sure to do. Then you're going to be iterating until your queue is empty. And you follow the simple instructions that Dr. Schwaller has given out. So let's see if we can find them here. So let's see, BFF, directed graph, directed driver. I don't know which one is his example. Network BFS. I don't know if he has examples on this sort of stuff. Has he done? Huh. Well, for Dijkstra's algorithm is a pretty simple algorithm. You're going to be using your min priority queue. You're going to iterate it, and then look at the neighbors of that vertex you're currently at. So, neighbor, I start here. This is my end. Blah blah. They all have infinities. And then I 1, 1, 1, 1. Well, I go here. I check the neighbors. Well, I'm connected to this man. I'm connected to this one. This has a weight of 1. This has a weight of 1. Then I pop this one. I push this one into my queue. Pop this one. Push this one into my queue. And then I'd be like, all right, this one has one neighbor. It's this one. So I pop this into the queue. I go to this one. Also, this has a weight of 2 now. I go to this one. This one has this neighbor. You can't relax that one. It's already relaxed. I get rid of that one. So that's mostly just going to be it. Now, the relaxing method, simple math. So the math revolves around the relax method is that the current weight that you're working on, So current weight. Weight. Plus the weight of both of them. Of both vertices is less than the weight of the second one. Less than the weight. You know, I should have wrote this one down. Of the second vertex. So the current weight you're working on plus the weight of both of these vertices combined is less than the second vertex that you input. Because you know how they're connected, you're adding them, blah blah blah. Now, you're going to be adding these guys, and then you're going to be using, you know, your breadcrumbs. Because, you know, it's BFS, it's similar to BFS. You're still using breadcrumbs here, I believe. Yeah, I use breadcrumbs. And then you're going to be using a decrease key on your second vertex. And that's mostly just it for the program. You run the program, and it should give you the shortest path depending on how you have everything set up. Because you call Dijkstra's algorithm, you set your current, you know, vertex as the last one, and you iterate backwards. Like, oh, current is not equal to start, change this map. And that's mostly just it for that. So, if you guys have any questions, leave something in the comments, and I hope you guys enjoyed. It's a very simple explanation of this code, and just follow the steps that you're given. Yeah, so thank you guys for watching, and hope you enjoy.